Hi, my name is René Williams. I'm assistant professor at the Molecular Photonics Group at the University of Amsterdam. And today we will discuss organic photovoltaic materials. We will see that the nanostructure of a thin film consisting of a mixture of an electron-donating conductive polymer and electron-accepting molecules, that the nanostructure strongly influences the efficiency of devices. This nanostructure is the result of the physics of phase separation during spin coating, and it can be influenced by a co-solvent. Improved molecular organization of the components within the film also enhances the power that can be generated through enhanced conduction, and it can be attained, for instance, by annealing. Now you all know that the sun is a huge source of energy, and there's a tremendous range of options to exploit it. One option is to use the sun to produce heat in what we call a solar furnace. That's a bit like focusing the sun through a magnifying glass, so you know it works. But we can also use the photons to do catalysis. But the most well-known way to harvest the energy of the sun is photovoltaics, and that we will discuss today. Whatever you do, this is the spectrum that is available, the solar spectrum. We see the black body radiation spectrum, that's the theoretical spectrum. In red is the practical spectrum on Earth. Okay, if we want to harvest all the photons, then we have to absorb them and basically convert them into electrons. But the band gap plays a very important role. So for instance, if the band gap is 500 nanometers, and we convert all these photons into electrons, then the maximum theoretical efficiency is about, let's say, 15%. We can get about 2.5 volts, but we will not get a lot of current. The power is the product of the voltage and the current. It has been estimated that about 50,000 terawatts that is hitting the Earth, and only 0.5% of that is stored by photosynthesis, by the plants. Now the human energy need is only 0.03% of what is available. We only need to harvest a fraction of the sunlight that's there. Now, if we want to convert the light of the sun into electricity, there's basically 3 options. There's silicon solar cells, but well, they are a little bit expensive. People try to develop alternatives, like for instance, perovskites, dye-sensitized solar cells, the Grätzel cell, and organic solar cells. Here we see an example of such an organic solar cell made by a Danish university spin-off company. And you see that it's plastic, it's flexible, it's colored, and these are the components. So it contains a polythiophene, we call it P3HT, and it contains a fluorine adduct, and that we call PCBM. Since people started using C60 as the electron acceptor and the electron conductor in organic solar cells, the field has gotten a huge boost. So C60 conducts the electrons and accepts the electrons. So the conducting polymers, they are used as light absorber, as the electron donor, and the material that conducts the positive charges, the holes. So just like in this children's game, where the hole can be moved easily, also the holes in conductive polymers are very mobile. They're radical cations, they can move. In 1992, Serdar and Woodall, they used femtosecond transient absorption spectroscopy to show an electron transfer between such a polymer, polyvinylene, we call it PPV, and C60, and it happened on a 40 femtosecond time scale. So they used very fast laser spectroscopy, and in 40 femtoseconds, an electron came from the photoexcited donor to the buckyball acceptor. And this was basically the first polymer fluorine solar cell. In fact, in 1993, I was at the Fluorine's conference, And my poster was hanging next to the one of Serdar. And I heard a very interesting discussion between him and another PhD student. Basically, they said, the cells, they perform better if you work more sloppy. Now, that sounds really, really strange, but basically, I now understand what they were saying in these days. If you would make an organic solar cell, you would do spin coating. So first, you would spin coat a layer of the polymer. So you dissolve the polymer in the solvent, you spin coat it on the surface, and then on top of that, you spin coat the fullerene. So you spin coat the C60 moiety. And of course, after the first spin coating, you dry your sample and you wait, maybe you put them in a vacuum oven, and then you put the next layer. So you make a nice sandwich structure, which basically was the strategy at that time. So what happens if you work sloppy? If you work sloppy, then you're not gonna wait, you're not gonna put it in an oven, you're just gonna spin coat one, and then 5 seconds later, spin coats the next. Now, if you work really, really sloppy, and you're very lazy, then you say, well, you know what? I'm just gonna put the polymer and the fullerene together and spin coat it like that. Now, that actually works the best, and that is what we call the bulk heterojunction. So if you spin coat your layer from a solution that contains both components, then during the spin coating, you get a material that actually works very well. This is what we call nanoscopic interpenetrating networks. You have a network of the donor and a network of the acceptor, and they form nanoscopic structure. But first, so what is happening in these kind of solar cells? So here you have the bottom electrode, the light goes through, it excites mainly the polymer because the C60 does not absorb a lot of light. Then you have electron transfer to the buckyball, to the C60 unit. The electrons are transported through a phase containing the fullerene. The positive charges are conducted through the polymers to the other electrode. So in that way, you have charge generation at the interface, electron conduction through the C60 phase, and hole conduction through the polymer phase. Here you see a representation of what they call this bulk heterojunction. So it is a phase separation where you get a fullerene phase and a polymer phase. And at the interface, the charge is generated. Then the electrons move through the buckyball phase, and the holes, they move through the polymer phase. That is the bulk heterojunction concept. We can also visualize the process like this. So we have the excitation of the donor, we have electron transfer to the acceptor phase, and then injection into the electrode. Here we have hole transfer to the other electrode. So the positive charge goes up, and negative charge goes down. Okay, the science behind organic solar cells, it's huge. And basically it has spurred from the overlap of 5 areas where Nobel Prizes have occurred. I already showed them, but here the fullerenes, the conductive polymers, electron transfer, and fast spectroscopy. Here we see the efficiency of organic solar cells. They rise over the years between 1985 and 2015, going from about 1% in 85 to about 12% in 2015. So there's a big development. We will discuss more recent data a bit later. The first cell was made by somebody from the company Kodak that also makes stuff that is related to photography. So today we will see that the efficiency of organic solar cells, that it is determined by the nanostructure, the nanoscale morphology, because that determines basically, or it's an important factor in the determination of the efficiency. And these studies, they were performed with this conductive polymer. It's again polyvinylene vinylene type, and this C60 adduct PCBM. These transmission electron microscopy pictures, they show that at about 88% of the fullerene, that the black fullerene phase in the film, it has about a dimension of about 50 nanometers. So here you see the scale. So these black balls, these black units are about 50 nanometer in diameter. That turns out to be the optimal domain size. So you see that at 60%, if there's 60% fullerene in your solution, then you don't see any structure. And at 90%, this fullerene phase is a lot bigger. This nanostructure is correlated to the device performance. Performance of solar cells with 80% fullerene, it is optimal. So here you see the percentage of fullerene. Here you see, well, some kind of efficiency scale, and it goes up from 60 up to 80. And then if you increase the fullerene content, the efficiency goes down again. And you also see it here at the other side. Also the incident photon to current efficiency, that also shows a clear maximum at 80%. And it tells you something about how efficient the photons falling on the systems, how they are converted into electrons. For this particular combination of polymer fullerene, 80% clearly is the maximum. And we also see that in the, what they call, in this graph where you see the efficiency versus wavelength. So you see you go from 20, 50, 60 at 80%. The current that is generated at every single wavelength is the highest. So again, there's a maximum at 80%. And that is due to these nanoscopic interpenetrating networks. So the efficiency of an organic solar cell, it is correlated to the nanostructure. And that is due to nanoscopic interpenetrating network. So we can, yeah, the network is the donor and acceptor is interpenetrating. You have a lot of contact area, and you have a lot of good domains or a good phase to transport the charges through. So that is a very important aspect of the organic solar cells. Okay, by using optical spectroscopy, we can get more insight into how these devices work. And if we look at the UV absorption spectrum, then we see the separate components here. You actually see that in the visible area, yeah, this paper comes from a physics group, so they put the wavelength in electron volts, but this is the low energy side. So C60 does not absorb a lot of light in the visible because it's so symmetric. So the symmetry makes the transition forbidden. If we look at the mixture, then you see that it's almost the same, only in the low energy region there's a small change, but this indicates that in the ground state, these molecules do not interact a lot. There's no strong interaction in the ground state. Now we can also look at the time-resolved emission. So the emission comes from is monitored from the polymer, and you see that at 0%, so the red line here, this is the emission of the polymer by itself. So it is on a nanosecond time scale. You see it is, well, a normal fluorescent signal with a lifetime of a couple of nanoseconds. This scale here is logarithmic. So a linear line on the logarithmic scale means it's an exponential decay. We will come back to that to remind you. Now we see that already at 2%, so if you put in 2% of your fullerene, the line changes a lot and it becomes a lot shorter. If you increase, then actually it remains just as short or as short as they can measure. So that means that already at 2% of fullerene in your polymer phase, all the emission disappears. And that's due to charge generation. But at 2% C60, the charges cannot move in the material. To remind you, if you look at the time-resolved emission, if you look at the decay of a state, you have to describe it with exponential functions. So this is a typical representation, for instance, here of a bi-exponential function. So it's with e to the power minus t over tau. And this represents a normal fluorescence decay. On a linear scale, it's a normal emission decay. And the lifetime is actually when the intensity has dropped 1 over e. So at about 36% of the signal for a mono-exponential decay. If there's a bi-exponential decay, then you have this kind of shape. So you have a spike in the beginning and then, for instance, a longer component. So this is just simulated, but it sort of shows you that this is a mono-exponential decay And at 30%, you actually see not only a short, but also something that is more long-lived. But we will not dwell on that. So you see that the emission is gone. It is quenched already at 2%. Now we can also have a look at transient absorption absorption of the excited state. And that's what we see here. Here we see the normal absorption and emission of the polymer. Now, if we take a look at the excited state, so that's a singlet state, if the excited state of the polymer, that has a spectrum like this. So that is the dashed line. That's the polymer by itself. Now here we see measurements of the excited state, so fingerprints of the excited state of the blend. So in the beginning, we see something that is very similar to this excited state of the polymer, to the singlet. But as time progresses, that's here. So we go from 15 to 30, 60, 100 femtosecond, it's femtosecond, yeah. So at 200 femtoseconds, the spectrum has changed totally. And now it is basically the same as a spectrum that is taken on a very, very long time scale, a millisecond time scale. And that indicates that you have formed the charges in the film. Within 200 femtoseconds, you have a spectrum that indicates that the charges are formed. It means that charges are generated at a very, very fast rate, and that is good. If rates are fast, then efficiency can be high. So this is absorption of the excited state, transient absorption, pump probe spectroscopy. This is such an equipment looks like this. And okay, the nice thing is that in this type of spectroscopy, you use the speed of light to delay one pulse of a laser relative to the other. So you have two pulses, they're correlated. So you focus them on one area, but one of them, he makes a little detour and then it arrives a bit later. So the whale, he had a concept that you use the speed of light to delay one pulse relative to the other. And this thing here, this thing moves during the measurement. That's the delay stage. And with this kind of spectroscopy, you can look at molecules, materials, you can get signatures of the excited state. Basically, first you take a normal spectrum, then you hit it with a laser, and then you can take a spectrum of the excited state that is formed. So here we see, so this is an example that the triplet state is formed. So you can get a fingerprint as a function of time of the absorption of the excited state. That is the technique that has been used here. And you can also visualize it like this. So you have a pump that excites the molecules or the film, and then you have a probe that sort of measures what is happening, and then you disperse it, you can get a whole spectrum. Next to time-resolved emission, you can also look at excited state absorption, pump probe spectroscopy. So that is what has been used here, and it tells you something about how fast these charges are made, and you can also measure how long they live in such a film. You can also do photocurrent. So photocurrent is basically current that is generated by shining a light. And from these experiments, charge transport is proven. If you increase the content of the fullerene up to 50%, then the charge can move through the film because the conduction, the photoconduction transient, has very long lifetime. So the charges are very long-lived when you increase the concentration of fullerene. So this implies that charges can move through this phase, through the fullerene phase to the other electrodes. We also see that even the polymer by itself, so it's just try to measure the photocurrent generated by the polymer itself, you see some signal, but it's very weak. Okay, by using a different solvent, you can also influence this nanostructure, and so you can influence the efficiency. So here they compare toluene with chlorobenzene, and you see in this electron microscopy picture that there's a big influence on the size of the aggregates. So in toluene, the aggregates are much bigger, they're a couple of 100 nanometers. In chlorobenzene, the aggregates are much smaller. These smaller domains, they give a higher efficiency. This is a current voltage plot. So if you shine light on the film cast from toluene, there's not a lot of current, but you can generate almost more than half a volt. If you take the other layer, then a lot more current is generated, almost twice as much. The voltage is basically almost the same, so that's related to the material properties, but the current is much higher. So that is influenced by the nanoscale morphology. So you can change the nanoscale morphology of organic solar cell by changing the solvent or even using a co-solvent, an extra solvent. And you can also heat a film for a limited time on the vacuum, and it can result also in an efficiency increase. So here you see this typical current voltage plots. So here, this is not a good cell. So if you heat your device for half an hour at 150 degrees, then the efficiency increases a lot. And you can see that from this current voltage plot. Using a different solvent can improve the efficiency, and you can also visualize that. So here we see that the contrast between the white and the black phase, it has increased. If you compare this picture A to B to C, in C, the picture is slightly different. Maybe it's difficult to see, but the white phase is more white and the black phase is more black. So that implies that there's a better phase separation. So the fluorine phase and the polymer phase, they are better separated. And annealing also improves the crystallinity of the domains. That is shown here. So this is X-ray diffraction. The increase of this peak, of a diffraction peak, this peak becomes stronger. Now that implies that there's more crystalline region, because in X-ray diffraction, only the crystalline regions give these sharp peaks. Annealing your sample, heating your sample at 150 degrees for half an hour, it increases the crystallinity of the polymer domains. The polymer phase becomes more crystalline. And that is better, that is improving the device efficiency, and it also improves the charge transport. So you again see that size domain, nanoscopic domains, and molecular organization, order, that it is very important for the properties. By using laser spectroscopy, people have shown that upon excitation of these donor molecules in green, that a charge is generated that is delocalized over multiple acceptor units. So this negative charge, it's not localized just on one buckyball molecule, but over several. So they did it with the Stark effect. It's a complex method, but correlates with what I just showed you on the X-ray diffraction. The radical anion, it's delocalized over several fluorine units in what they call a coherent state. The electronic wave function of the radical anion, it's delocalized. As I just showed you, some people have started, well, to sell these kind of products. Konarka, they were the first to do this. I also have some Konarka cells somewhere. And they did not last long because they focused on building integration. And that's not the thing to do. Mitsubishi, they held the world record of organic photovoltaic materials from 2012 to 2015 at about around 11%. This record was broken in 2016 by a group from Hong Kong. And they used, well, what they call a green solvent. They used this phenyl naphthalene, a very, very weird solvent, but it's not very volatile. So in that respect, you can imagine that they call it green. Here you see the IV curve. So again, you see that using phenyl naphthalene as the co-solvent, as some extra solvent, you can generate much more current in such a cell compared to the other benzene solvent. And also the external quantum efficiency, so basically how many photons are converted into electrons. Also that curve is much higher at every wavelength that is absorbed. So you can understand that the phenyl naphthalene co-solvent, that it has a very good effect. Solar fidelity, they sell these kind of things for hiking. If you go to the mountains, you don't have a socket. And Infinity PV is a Danish spin-off company. They also sell some products. You can buy them if you do your best and look on the internet. Now, recently, the focus has shifted from fluorine acceptors to other molecular components. And here we see that recent efficiencies, they've even reached about 18%. Around 2016, the non-fluorine materials, they overtook the buckyballs, and they used these rather special conjugated acceptor molecules that absorb a lot of light, but they also give charge separation and a small driving force. So there's only a small offset in energy relative to the singlet excited state. But so you see that, well, all four of them are a certain class of molecules. So they are highly conjugated. They have cyano groups, so there's acceptor groups, there's donor groups in the middle, a lot of solubilizing alkyl tails. And so this is the recent development in these fields. We have seen that the structure on the nanoscale and the molecular order within a thin solid film, that is extremely important for the properties. We need nanoscopic interpenetrating networks with a high crystallinity for the best performance. By using time-resolved spectroscopy, we can get a better understanding of what is happening in these blends. And recent developments with non-fluorine electron-accepting units, they give organic photovoltaic materials a bright future in niche markets. Thank you. This is something about organic solar cells and nanostructure. So it is a photoactive nanomaterial. It is technology because you can buy the products, they are on the market. Also, I can say that in related area, in dye-sensitized solar cell, a company called Rico, which also make photocopying devices, they have just put on the market a dye-sensitized solar cell, which is totally solid state. So you can see that also industrial companies at the moment, they're putting a lot of effort in making these kinds of materials, where also the nanostructure is important for the efficiency.